When I look at Mars, I see a planet that almost made it. A world that started with many of the same basic ingredients as Earth, but ended up cold, dry, and with an atmosphere so thin that liquid water can barely exist at the surface. In this monologue, I want to explain, step by step, how Mars lost most of its atmosphere, what we actually know from data, what we are still trying to understand, and how this connects to gravity, space-time, and even the large-scale evolution of the universe. I will stay with real physics, no invented forces, no hidden magic, just what we can defend with observation and theory. I start with the simple fact. Today, the surface pressure on Mars is about 6 millibars on average. Earth's is about 1,013 millibars. So Mars has less than 1% of Earth's surface pressure. Yet we see dried up river valleys, deltas, lake beds, and mineral evidence that liquid water once flowed on the Martian surface for long periods. To have stable liquid water, Mars must once have had a thicker atmosphere and higher surface pressure. So the natural question is, where did that atmosphere go? To answer that, I need to start with gravity, because gravity is the first gatekeeper for any atmosphere. Gas molecules in an atmosphere are in constant motion. Their speeds depend on temperature and molecular mass. The hotter the gas and the lighter the molecule, the faster it moves. A planet's gravity must be strong enough that the typical molecular speeds are well below the escape velocity. If not, molecules drift away into space over time. Escape velocity is set by the planet's mass and radius. It comes from Newtonian gravity, or more rigorously from general relativity in the weak field limit, but the simple formula works well here. Mars has about 11% of Earth's mass and about half its radius. Its escape velocity is about 5 kilometers per second. Earth's is about 11 kilometers per second. This means that for a given atmospheric temperature, a larger fraction of molecules on Mars sit in the high-speed tail of the Maxwell-Boltzmann distribution and can escape to space. This process is called Jeans escape. It is one of the basic thermal escape mechanisms. Jeans escape is most efficient for light gases like hydrogen and helium. On Mars, hydrogen produced by the breakdown of water or other molecules can reach escape speed more easily than on Earth. Over billions of years, this steady leakage can remove a lot of hydrogen. When hydrogen is lost, water is effectively lost because water is 2 hydrogens and 1 oxygen. Oxygen can react with the surface and get locked into rocks. So even slow thermal escape can permanently dry a planet. But gravity alone does not explain the full story. Venus has a mass similar to Earth, a thick atmosphere and no global magnetic field. Yet it did not lose its atmosphere the way Mars did. So I need to add more pieces. The sun's radiation, the solar wind, the planet's magnetic field, and the internal geophysics that drive that field. The sun is not just a source of light and heat. It is a source of high-energy photons, especially in the ultraviolet and X-ray range, and a stream of charged particles called the solar wind. The solar wind is a plasma of protons, electrons, and some heavier ions. It flows outward at hundreds of kilometers per second, guided and structured by the sun's magnetic field. Near Earth's orbit, it is already a supersonic flow in plasma terms. It carries energy and momentum. When it hits a planet's atmosphere, it can strip away gas. On Earth, we are largely shielded by our global magnetic field. Our field is generated by a dynamo in the liquid outer core. Conducting fluid in motion, coupled with rotation, sustains a magnetic field that extends far into space, forming the magnetosphere. The solar wind is deflected around this magnetosphere, and only a fraction of particles manage to penetrate down to the upper atmosphere. There is still atmospheric loss, but it is relatively modest. On Mars today, there is no global magnetic field. There are only crustal magnetic patches, fossil remnants of an ancient field. So the solar wind can interact directly with the upper atmosphere over large regions. It can pick up ions and drag them away. It can heat the upper atmosphere, driving non-thermal escape processes. This is where modern spacecraft data becomes crucial. NASA's MAVEN mission, the Mars Atmosphere and Volatile Evolution spacecraft, has been orbiting Mars since 2014. Its main job is to measure the current rate and mechanisms of atmospheric escape. It carries instruments to detect ions, electrons, magnetic fields, and neutral particles. From MAVEN, we know that the solar wind is actively stripping the Martian atmosphere today. We see ions being picked up and accelerated along magnetic field lines. We see atmospheric loss rates that increase dramatically during solar storms, when the sun's activity spikes and the solar wind becomes more intense. By measuring the current escape rates and combining them with models of the sun's past behavior, especially when the sun was younger and more active, we can estimate how much atmosphere Mars has lost over time. Early in the solar system, the young sun emitted much more extreme ultraviolet radiation. That radiation heats and expands the upper atmosphere, making it easier to strip. With no strong global magnetic field, Mars was exposed. MAVEN data suggests that a significant fraction of Mars's original atmosphere, perhaps the majority, was removed by these solar-driven, non-thermal escape processes. This leads to the next key question. Why does Mars lack a global magnetic field today, and when did it lose it? Planetary magnetic fields are closely linked to internal heat and rotation. A dynamo requires a conducting fluid, like liquid iron, that is convecting and rotating. Early Mars was hotter due to formation energy, radioactive decay, and possibly large impacts. It likely had a molten core and a functioning dynamo. The crustal magnetic fields we see today record that ancient field. At some point, the dynamo shut down. Perhaps the core cooled and partially solidified. Perhaps convection patterns changed. The details are still an active research area. Once the dynamo stopped, the global magnetic field weakened and eventually disappeared. The timing matters. If Mars lost its dynamo early, then for most of solar system history, it was exposed to direct solar wind stripping. Crater counting and magnetic measurements suggest the dynamo may have shut down more than 4 billion years ago, but the exact timeline is uncertain. That uncertainty feeds directly into models of atmospheric loss, because the earlier the field vanished, the longer the atmosphere has been vulnerable. So far, I have mentioned thermal escape, solar wind stripping, and the loss of a magnetic field. There are more processes. High-energy photons from the sun can ionize and dissociate atmospheric molecules. Energetic particles can knock atoms out of the atmosphere in a process called sputtering. When a high-energy ion from the solar wind hits the upper atmosphere, it can transfer enough momentum to eject atoms into space. Some escape processes are driven by chemistry and photochemistry. For example, carbon dioxide, the main component of Mars's atmosphere, can be broken apart and recombined into species that are more easily lost. We also know that some of the atmosphere is not lost to space, but sequestered in the surface and subsurface. Carbon dioxide can freeze into polar caps. It can react with rocks to form carbonates. Water can be trapped as ice in the ground or as hydrated minerals. So when we talk about atmospheric loss, we must distinguish between loss to space and loss to the solid planet. Both reduce surface pressure and change climate. How do we know that Mars once had a much thicker atmosphere? Several lines of evidence converge. Orbital imagery shows valley networks and delta structures that are best explained by long-lived liquid water flowing on the surface. Rover missions like Curiosity and Perseverance have found sedimentary rocks that form in standing water, and minerals like clays and certain sulfates that require water to form. These features indicate not just brief catastrophic floods, but sustained wetter conditions. We also have isotopic evidence. Isotopes are versions of an element with different numbers of neutrons. Lighter isotopes escape more easily than heavier ones. So if a planet loses atmosphere to space over time, the remaining atmosphere becomes enriched in heavier isotopes. On Mars, the ratio of deuterium to hydrogen in the atmosphere is much higher than in Earth's oceans or in the Sun. Deuterium is a heavier isotope of hydrogen. This enrichment tells us that Mars has lost a large amount of hydrogen and therefore a large amount of water. Similar isotopic signatures appear in nitrogen and other elements. The pattern matches expectations from atmospheric escape. By combining geomorphology, mineralogy, isotopes, and direct escape measurements, we build a consistent picture. Early Mars likely had a thicker atmosphere, higher surface pressure, and stable liquid water. It may have been habitable for microbial life. Over time, because of its lower gravity, smaller size, cooling interior, loss of dynamo and magnetic field, and ongoing exposure to a variable sun, it lost most of its atmosphere and much of its water. What remains is a cold desert with a thin, mostly carbon dioxide atmosphere. Now I want to connect this to the broader framework of gravity, space-time, dark matter, and cosmic expansion. On the scale of a planet, we usually use Newtonian gravity. But Newtonian gravity is an approximation to general relativity, which describes gravity as the curvature of space-time caused by energy and momentum. Mars's ability to hold an atmosphere is ultimately a question of how strongly it curves space-time near its surface. The deeper the gravitational well, the more energy a molecule needs to escape. In the language of relativity, a molecule climbing away from the planet is moving uphill in space-time. Mars curves space-time less than Earth does because it has less mass. This is a local manifestation of the same principle that structures galaxies and clusters on large scales. Dark matter, which we infer from galaxy rotation curves, gravitational lensing, and the cosmic microwave background, dominates the mass budget of galaxies. It curves space-time, creating deep potential wells in which gas can collect, cool, and form stars and planets. Without dark matter, the early universe's tiny density fluctuations would not have grown fast enough to form the structures we see today. So the existence of Mars and the Sun already assumes a cosmic background shaped by dark matter. The dark matter halo of our Milky Way holds the galaxy together and sets the gravitational environment in which the solar system orbits. But does dark matter have any direct role in Mars's atmospheric loss? As far as we know, no. Dark matter interacts primarily through gravity. It does not collide with gas molecules in the atmosphere in any significant way. Its density on solar system scales is extremely low. The gravitational field of dark matter near Mars is almost uniform and very weak compared to Mars's own gravity and the Sun's gravity. So dark matter is crucial for the large-scale existence of galaxies and planetary systems, but it does not strip or protect Mars's atmosphere. Dark energy is even more subtle here. Dark energy is the name we give to the observed accelerated expansion of the universe. On the largest scales, space-time is not just expanding, the expansion is speeding up. This is inferred from supernova observations, the cosmic microwave background, and large-scale structure. In the simplest model, dark energy behaves like a cosmological constant, a uniform energy density filling space with negative pressure. It drives acceleration but is extremely weak on small scales. The expansion of the universe, even with dark energy, does not pull apart atoms, planets, or solar systems. Gravitationally bound systems decouple from the Hubble expansion. The gravitational and electromagnetic forces inside these systems are far stronger than the tiny effect of cosmic expansion. So Mars's atmosphere does not leak away because the universe is expanding. The molecules in the atmosphere are bound to Mars by its gravity. Cosmic expansion only matters on scales where gravity is too weak to hold things together, like the voids between galaxy clusters. In that sense, the fate of Mars's atmosphere is almost entirely a local story. It is set by Mars's mass, its internal heat, its magnetic field history, its distance from the sun's activity, and the physics of gas escape. Dark matter and dark energy set the stage for the existence of the solar system, but they are not the actors in this particular drama. However, I can still place Mars in the larger context of cosmic time and the fate of the universe. The processes that stripped Mars's atmosphere are time-dependent. The sun's luminosity and activity evolve. Early in its life, the sun was dimmer in visible light, but more active in high-energy radiation and solar wind. Over billions of years, its core composition changes as hydrogen fuses into helium. Its luminosity slowly increases. In about 1 billion years, Earth itself may become too hot for liquid water due to this brightening, regardless of atmospheric escape. Mars, being farther out, will warm too, but its thin atmosphere will limit any stabilizing greenhouse effect. In about 5 billion years, the sun will leave the main sequence and become a red giant. Its outer layers will expand, and the inner planets will be heavily affected. Earth may be engulfed, or at least scorched and stripped. Mars's orbit may shift, and any remaining atmosphere or ice will be altered or lost. Eventually, the sun will shed its outer layers and leave behind a white dwarf. At that stage, any remnant of Mars will orbit a dense, cooling stellar core. The atmospheric story of Mars will essentially be over long before that, but the solar evolution sets a hard upper limit. On even larger timescales, dark energy dominates. If dark energy is a cosmological constant, the expansion of the universe will continue to accelerate. Galaxies not gravitationally bound to us will recede beyond our observable horizon. Star formation will slow as gas is used up. Stellar remnants will cool. Black holes will eventually evaporate via Hawking radiation on timescales far longer than the current age of the universe. In that distant future, the detailed history of Mars's atmosphere will be a tiny, local fluctuation in a universe that has moved far beyond star-forming epochs. This contrast is important. On planetary scales, we deal with processes like atmospheric escape, volcanism, impacts, and solar wind. On cosmological scales, we deal with the growth of structure from quantum fluctuations, the role of dark matter, and the acceleration driven by dark energy. The laws of physics are the same, but different terms dominate in different regimes. Gravity is the common thread, from the binding of an atmosphere to the binding of galaxy clusters. I also want to talk about how we know these things, not just what we think is true. For Mars, we have orbital spacecraft, landers, and rovers. We have spectroscopic measurements of the atmosphere, radar mapping of the subsurface, and in situ analysis of rocks and soil. MAVEN measures ion escape. Mars Express and other missions have probed the upper atmosphere and ionosphere. Isotopic ratios are measured with mass spectrometers. These are direct data. We combine those with physical models. We use fluid dynamics to model atmospheric circulation. We use kinetic theory to estimate escape rates. We use magnetohydrodynamics to simulate the interaction between the solar wind and the Martian ionosphere. We use thermal evolution models to track how Mars's interior cooled, how its core changed phase, and how its dynamo might have shut down. These models are tested against observations. If a model predicts escape rates that are too high or too low compared to MAVEN data, we adjust the physics or the input parameters. For the sun's past activity, we do not have direct observations from billions of years ago. Instead, we study young sun-like stars at different ages. We measure their X-ray and ultraviolet output, their rotation rates, and their stellar winds. We infer how the sun likely behaved when the solar system was young. This is an example of using the broader universe as a time machine. Different stars at different ages give us snapshots along the evolutionary track. For dark matter and dark energy, the evidence comes from very different observations. Galaxy rotation curves show that stars orbit faster than can be explained by visible matter alone. Gravitational lensing shows mass-bending light where there is little visible matter. The cosmic microwave background encodes the imprint of early universe fluctuations and the total matter and energy content. Type Ia supernovae at different redshifts show that the expansion of the universe has accelerated in the last few billion years. These are independent lines of evidence that converge on a universe dominated by dark matter and dark energy. The key point is that we apply the same scientific method at all scales. We observe, we model, we test, we refine. For Mars, the data are immediate and local. For the universe, the data are distant in space and time. But the logic is the same. What remains unknown about Mars's atmospheric loss? Several important things. We do not know the exact initial inventory of volatiles on Mars. How much water and carbon dioxide did it start with? Was it delivered mostly by impacts, or did it outgas from the interior? We have models, but they are not tightly constrained. We do not know the precise timeline of the Martian dynamo, when it started, how strong it was, and exactly when and why it shut down. That timeline controls how long Mars had a magnetic shield. We also do not fully understand the early sun's wind and radiation history. Stellar analogs help, but individual stars vary. Small differences in early solar activity can produce large differences in long-term atmospheric loss. We are still refining models of non-thermal escape, sputtering, ion pickup, and photochemical escape. MAVEN has improved our understanding, but extrapolating billions of years into the past always carries uncertainty, and we do not yet know how typical Mars is. Are Mars-like atmospheric losses common on small rocky planets around other stars, especially around active red dwarfs with strong stellar winds and flares? Or is Mars an unusual case, shaped by specific details of its formation and history? Exoplanet observations are starting to probe atmospheres of small planets, but we are only at the beginning. When I connect Mars to dark matter and dark energy, I am reminded that local and cosmic stories are intertwined but not identical. Dark matter and dark energy set the large-scale gravitational and expansion background. They allow galaxies and stars to form. Within that framework, ordinary matter, radiation, and planetary processes do the detailed work. Mars's lost atmosphere is written in the language of gravity, plasma physics, and geophysics, not in the language of cosmic acceleration. Yet both levels are part of one consistent physical universe. So I end with a concrete, unresolved scientific question. We know that Mars lost of its atmosphere, and we have identified the key mechanisms. But we still do not know with high precision the relative contributions of each process over time: thermal escape, solar wind stripping, sputtering, photochemical escape, sequestration into the crust, and catastrophic losses from large impacts. In other words, if I could rewind Mars to its early state and watch it evolve and fast forward, how exactly would the atmospheric pressure curve change with time, and which physical process would dominate at each stage? That detailed atmospheric loss history remains an open problem we are still working to solve.